Okay, so welcome everybody to this new DaSCI seminar. Today is my great pleasure to introduce Dr. Ricardo Vinuesa. He is an associate professor at the Department of Engineering Mechanics, KTH Royal Institute of Technology in Stockholm. He is also vice director of the KTH Digitalization Platform and lead faculty at the KTH Climate Action Center. He studied mechanical engineering at Universidad Politécnica de Valencia and received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. Dr. Vinuesa has received, among many other grants and awards, an ERC Consolidator Grant and the IIT Outstanding Young Alumnus Award, and is leading several large Horizon Europe projects. Today, he will talk about the role of artificial intelligence in achieving the Sustainable Development Goals. I want to thank again Professor Vinuesa for very kindly accepting our invitation, and whenever you are ready, the floor is all yours.
Thank you very much for the introduction and for the very kind invitation to present here. It's my pleasure. So yes, today I'm going to be discussing some of our earlier and more recent work on the role of AI to achieve the SDGs, the Sustainable Development Goals. This is research funded by the ERC, the European Research Council, and also Digital Futures, which is a research organization within KTH in Sweden. So I'm going to first discuss how to use AI for sustainability, kind of in a broader sense. And then at the end of the talk, I will mention some more detailed examples. So I will get a bit more technical, and hopefully both parts can be helpful for different people in the audience. So how can we use AI for sustainability? We can maybe start with a motivation, of what AI has been achieving over the past years. Of course, in computer vision, machine learning has been really exhibiting a lot of success. There is the ImageNet challenge, which really shows that AI algorithms can be much better than humans at classifying and identifying images. There's many areas where AI is growing exponentially: predictive tests, speech recognition, data analytics, finance. And maybe one early example where a machine could beat a human at an intellectual task was in 1997, when the IBM Deep Blue machine defeated Garry Kasparov in chess. He was the world champion at the time. He didn't take it very well, actually. He got quite upset and he complained a lot. Actually, some things with reason, because he was asking about the code and he was wondering whether Deep Blue was cheating. That was kind of like an early example of the need for explainable and interpretable AI, which will be one of the aspects that I will be talking about later. Turns out that chess is a relatively simple game. So almost with brute force computing, by trying combinations, you can play pretty well chess. The complexity of a game can be calculated as the number of moves that you can have in a particular turn raised to the power of the number of turns that a typical game has. So if you do n to the power of t, you can see that the game of chess has this number over here. And this is much lower than the game of Go. The game of Go, which has become quite popular in the past years because IBM DeepMind has really, sorry, not IBM, the DeepMind team has actually been able to develop algorithms to play Go very well. And this was a milestone that was not expected to be achieved within decades. So this game of Go, which is not possible to be played with brute force computing, but rather with some strategic kind of thinking. Well, actually, that was a milestone that was achieved by deep learning models now 6-7 years ago. So the Google team, not IBM, but Google, the Google team of DeepMind, they were able to train an algorithm to play the game of Go based on showing the best human players. So this algorithm was learning from the best human players. And this algorithm was able to defeat Lee Sedol, who was the world champion of Go some years ago, by 4-1. This was published in Nature in 2016. Maybe even more remarkably, in 2017, so now 7 years ago, they developed a new algorithm called AlphaGo 0, which was not given the rules of the game of Go. It was just given some guidelines on how to play, they didn't show any human gain to this algorithm, and just by playing against itself, it could really improve its performance exponentially using an algorithm called reinforcement learning. So reinforcement learning is actually a very, a helpful deep learning-based tool where you can iteratively improve your performance, as you can see in this figure here at the bottom. No? So in less than 2 days of training, this AlphaGo 0 was able to defeat the algorithm that was trained based on human knowledge by 100 against 0. Not only that, but it was able to come up with completely new strategies that were not maybe foreseen with thousands of years of human knowledge on this game. No? So in certain tasks, AI can actually outperform humans, so far in very narrow and concrete tasks. Now, if we focus on the SDGs, the Sustainable Development Goal Agenda of the United Nations, this is the 2030 agenda adopted by all the United Nations members in 2015, and it's a shared blueprint for prosperity for all the people in the planet. The SDGs include very wide range of topics, from ending poverty to economical growth. And of course, there's environmental aspects that need to be fulfilled within those boundaries. And this very broad range of topics is mapped into 17 goals, the SDGs, and 169 targets, which are considered to be sub-goals of the bigger ones, basically. Right? So this SDG agenda, and I hope that many in the audience are familiar with it, really is the roadmap to sustainability of the planet. Now, some years ago, and this is maybe 2017, 2018, something like that. So quite some years ago, I was having lunch with a colleague at KTH, with Francesco Fusionerini, who is co-author of this study. And we were wondering whether there is published evidence of AI acting as an enabler or an inhibitor of sustainability of each of the SDG targets. And we realized that there wasn't such a study, that had not been done. So of course, if we wanted to solve this question, because we're curious scientists, we required a quite multidisciplinary team to be able to tackle all the broad range of areas of knowledge required by the 169 targets. No, we would need experts in many, many different areas, and also artificial intelligence, obviously. Now, this study got published in Nature Communications in 2020, and it became a bit of a reference study for AI and sustainability. It has impacted the AI Act and the discussions on sustainability and technology. And it really started as a fun lunch conversation. So sometimes these spontaneous ideas are things that can contribute a lot to the community. So we assembled a team of 10 people, 5 men and 5 women from all over the world, with experience in engineering, in applied AI, in theoretical and more fundamental AI, interaction design, ethics, economy, experts in biodiversity, in ecology. We had also Max Diekmark from MIT, who is a visionary on AI and its future, and Francesco Fusionerini, the last author, together with me, who led also the study, together with me, experts in sustainability and analysis. So this was the team that we put together to really tackle this question. What we did was to divide the 17 SDGs into 3 main areas. This is a quite common classification into society, environment, and the economy, so that we could look at the results in a bit of a more holistic way. And this is the process that we followed. So we went target by target, all the 169, and we assigned a group of experts with knowledge on those targets from that SDG to make a first assessment based on the literature on whether AI can be an enabler or an inhibitor of that particular SDG. So in this example, and by the way, this Excel that you can see here is the supplementary material that we have in the article. So if you click in the Nature link, there is this very long list where for each of the 169 targets, we have 2, 3, 5, sometimes 10 references justifying our argumentation. So in this particular case, for target 1.1, we find evidence of AI being both an enabler, but also an inhibitor of that particular target. And we write a reasoning, we write a paragraph motivating our assessment. Now, the experts, in this case, Simone and so we could actually define these experts. who had expertise in the particular SDG. Now we had a team of reviewers, no? In this case, Yolanda and myself. There was an iterative process, what we call an expert elicitation, where the reviewers had to question and poke holes. This is like a red team on the initial assessment of the experts. And then we had this iterative process such that we could converge and all agree on the assessment for that particular time. So we did this for 169 targets with workshops, many in-person and online calls. Really a quite long process, but very, very rewarding and interesting. So these are the results that we obtained. 79% of the targets can be positively affected by AI, whereas 35% of them can be negatively affected by AI. And of course, this in principle throws an optimistic picture, although we should not underestimate the negative effects because, of course, even one target being negatively affected could have cascading effects leading to a very negative overall picture. So we should be aware of the negatives as well. But in principle, there is positive potential. The environment seems to be the area with the highest positive potential, and the society seems to be the area with more threats and more concerns. So this is kind of like a big picture result of our analysis. But we can look at this in a bit more detail. What you can see here on the left, I'm showing you for each of the SDGs, the percentage of targets that is positively affected by AI. And on the right, the percentage of targets that is negatively affected by AI for each of the SDGs. And you can see that there are lighter lines, lighter colors, and darker colors. The lighter colors are the ones that are obtained when at least one reference documents positive or negative effects. Then we have the green, the light green and light yellow lines over there. And the darker colors are obtained by taking into account the strength of the evidence. Okay, that's kind of like the next conclusion. So we divided all the references into 4 categories: A, B, C, and D, where A are the references with more sophisticated methods and more capabilities of being generalized, and D are the most theoretical and speculative references. So we had weighting factors going from 1 to 0.25, meaning that when we take into account the strength of the evidence, we are actually having, well, instead of one full target being completely affected, if there is a D reference, then we have only 0.25, basically, right, on that particular interaction. So we go back to the previous results. The dark colors, the dark area, by definition, is going to be smaller or equal than the light area, right? And in fact, by analyzing the regions where there is a biggest reduction from the light color to the dark color, we can see areas of research gaps, right? Because those are areas that are basically assessing studies that are more speculative, that require more research. And what is interesting is that the areas with the highest reduction are the negative effects of AI on the environment and the society. So if you look at the right panel, the reduction on the environment and the society is very pronounced when I take into account the strength of the evidence. And on the positives, the effect on the economy, that's the most speculative. So there is a very big research gap on the positive effects of AI on the economy. So that's another conclusion, another take-home message to keep in mind in terms of what we can understand from this. Okay. Now, overall, what are the, of course, if you go to this reference in Nature Communications and you go to the supplementary material, you will see all the examples. We have hundreds of examples there, but, and of course, this is now 4 years old. So some of the examples have been updated later on. Surprisingly, we predicted some things that have happened. So, I mean, we had a bit of a crystal ball, so we could have a bit of a prediction of the future. But overall, the positive effects are essentially due to new technology that is enabled through AI. So AI is allowing us to do something that was not possible before. One example, effect of AI to enable SDG 1 or no poverty through analysis of satellite data with convolutional neural networks, with computer vision, basically. So you can analyze the satellite data to predict regions of poverty. Negative effects, for example, on SDG 10 on inequalities. So most of the negative effects have to do with an unequal access or an uneven distribution of resources that are going to exacerbate the current inequalities that we have. Okay, so those are kind of like the two main examples. Important thing to keep in mind, and this is another study that we published a year later after a workshop at KTH on basically expanding some of these conclusions with Max Diekmark as well. Effects on SDG 5 on gender equality. There is a gender data gap because a lot of these models are trained on data from men. This has important implications, for example, in medical devices and also in speech and face recognition. So there's a data gap to be fixed. And there is a gender equality gap in AI professionals. So the workforce itself is biased, right, towards men. And of course, this is important for many reasons, but also because the design of these AI systems comes with some decisions of what features are going to be used, what training data, what type of algorithmics, which, of course, if we have mostly men in the workforce, these are going to be influences the way that these algorithms are being built, right? So there's two important gaps in terms of SDG 5 of gender equality that need to be fixed if we want AI to be beneficial for all, basically. Now, some more examples, and this is something that is actually quite interesting and has really led a lot of my work currently in the KTH Climate Action Center, which has to do with energy and climate action. So AI has the potential to achieve basically all the targets from SDG 7 on clean energy and almost all the targets in SDG 13 on climate action. But there are big problems associated with the energetic consumption of these AI algorithms, right? What happens is we are having currently a consumption. So ICT, information and communication technologies, are around 1% of the overall electricity nowadays. But by 2030 and beyond 2030, this is expected to increase by 20, even 30%. So the energetic consumption of these systems is massive, and they are very data hungry. In this regard, we should be using AI more in a smarter way, right? We should not just feed large amounts of data and increase the amount of parameters, particularly now with these large language models. Transformers and self-attention are maybe not the most sophisticated mechanisms. We should be able to embed physics in our models. So we are modeling a particular phenomenon with some physical properties or symmetries. We should include inductive biases such that we can accommodate for those properties in the model that we are actually developing. So that will certainly reduce the environmental footprint of your model, and that will also make it possible to learn those physical properties to a higher accuracy. So that's one lesson in terms of environment. There's some interesting considerations in the context of SDG 9, which has to do with innovation and industry. There's many new opportunities enabled by AI in terms of optimization of electricity usage, better models for bank performance, smart cities, being able to split complex tasks into simpler ones. And some of the negatives have to do similarly to before, to uneven access to the work resources. If we have low qualification, we're going to lose jobs, exacerbate inequalities, and displacement of tasks from developing countries to other regions. So that's a challenge. In the context of education, SDG 4, there's again opportunities from AI, which have to do with intelligent tutoring and smarter tools. I have some work where we're using augmented reality together with data to improve the student performance. But of course, this induces, again, biases. If the teachers are not trained and prepared to use this technology, if we have issues with data protection, and we have conflicts between these AI tools and the local cultures, then the effectiveness of the educational principles is going to be diminished. So there's many considerations here to keep in mind. Again, quite some potential, but some caveats to consider. Other risks, I guess. And again, this is something that we wrote before COVID, before Russia, before any of this. But of course, we were already thinking about some possible polarization of the society and, being able to influence elections, being able to influence the public opinion negatively. I mean, these AI systems they really can have a big impact on the inequalities, but also on SDG 16, on strong institutions, peace and justice. No? So we argue that regulatory oversight is important, but it's more important regulatory insight. So to involve experts, to involve people who know what AI can and cannot do in the process of developing regulations and in this dialogue that is affecting everybody. It's not only about the companies that are developing these large language models. It's not only about the EU developing the AI Act. It's everybody's concern, because this technology is going to affect us more broadly in the present and in the mid and long term. So this global dialogue is actually very important. I would like to also mention another work that we did in the context of COVID. This was in 2020, publishing results in engineering. This was about digital contact tracing. This has implications on SDGs 3 on health and 10 on inequalities. At that time, we argued that it was very important to use decentralized data gathering processes. And at that time, the DP3T protocol was key, and many of these apps were able to implement it. We developed basically a guide of how you should be deploying these apps, no, in terms of their impact on the citizens, the technology, and the governance. And we ranked many of these apps. Turns out that the one in the UK was actually really bad. And more or less at the same time as when we were developing this article, they changed from a centralized to a decentralized data gathering technique, which made us very happy. Essentially, where most of these apps failed was in the governance. Even the best apps ranked quite low in governance. So the way that you are from the government deploying this technology, right? And the reason, one of the main reasons, if not the most important, why these apps didn't really have a big impact on the handling of the pandemic was the lack of a good communication strategy by the governments, right? There was a bit of misinformation and fear and data. I mean, people are downloading apps that send their data all over the world to God knows where, right? And they don't care. And with these apps, well, maybe the communication regarding data should have been better, right? But that's maybe a lesson that we can learn. So data-driven methods can have implications also on everybody's lives, right? And if we deploy the technology properly from the government point of view, we can actually make a difference. The interactions that I was talking about before in terms of the different SDGs and how can AI affect them can be summarized like this. So we have the technology, and in this figure, the thickness of the arrow indicates the speed of change. So technology is changing very quickly. The individuals are lagging behind, and the government, in terms of standards and regulations, are lagging behind individuals, right? So there is something to be changed here in these dynamics of interactions, because otherwise this will not be really used for the best benefit of everybody. And I was talking about interpretability before. This is a commentary piece that we published now 3 years ago in Nature Machine Intelligence. Deep learning models are in general black boxes. They lack interpretability. We don't know how the input is connected with the output. There are methods for explainability, like SHAP and saliency methods. But interpretability, and this definition is a bit difficult to converge to, but let's say that in an interpretable deep learning model, you can actually see exactly how the input and the output are connected, no? And here, there is some interesting work by Cranmer and others using symbolic regression, where you can actually end up with an equation that is reproducing the performance of the network. Going back to the example of the satellite, we can go here as an input, we can see, well, the image from the satellites from different areas. A CNN, a convolutional neural network, is going to be using, well, basically activation maps, right? So we're going to see what parts of your input are going to be used to make the predictions. And the prediction will be a number, P, which is the predicted amount of money in dollars per capita and per day. And if that number is below a certain threshold, then the area is considered to be poor or at the risk of poverty. Now, with symbolic regression, with this interpretable deep learning framework, you can come up with an equation, a symbolic equation, which connects P, this amount of money, with certain features of your input. So, for example, the amount of light during the nights, the amount of roads, the distance to nearby cities, in such a way that you can see the relative importance of these various parameters, so you can predict not only the poverty now, but its temporal dynamics, right? And in such a way, you can hopefully gain insight to coordinate more adequately international actions. So that's a bit what we are going after here. So in this commentary piece in Nature Machine Intelligence, what we argue is that you cannot really use AI models for sustainability if they are not interpretable, meaning that they are transparent and accountable, basically. Some more recent work that we are very excited about is on using large language models, natural language processing, to try to understand the sustainability agendas. So in particular, what we are using is large language models to find synergies and trade-offs among all the SDGs. And of course, this has been done in the past. Experts have, got together and through expert elicitation discussed this. But many of these connections are hidden or unobvious. So there's bias based on the area of knowledge of the experts. And of course, the experts are going to read a bunch of papers, but with LLMs, we can read hundreds of thousands of papers and establish these connections in a bit of a more unbiased way. So this is work that we're currently developing with the idea of classifying the articles and also research projects and policy documents into the various SDGs, finding synergies and trade-offs among the different SDG targets, and then through optimization, develop optimal policy decisions. So again, this is ongoing work. We're very excited about it, and we think that it can be a transformative path to policy development. Also, last year, there was a bit of big impact through the Future of Life Institute, where Elon Musk and others started this open letter for a pause on large AI experiments, basically. Now, this was a bit of we wrote a couple of commentary pieces on this, one in Frontiers in Computer Science, where we basically argued that, basically stopping research is not going to help us to find the solutions to AI development. Probably from research itself, an adequate regulation is how we are actually going to solve these problems. And then we published also in Nature Climate Change. Francesca La Rosa was the main author of this. Another commentary piece where we argue that LLMs are actually helping massively in terms of tackling the climate emergency. We're really developing completely new strategies, completely new policy ideas through AI in order to tackle climate change. Right? So we think there's quite some positive potential here to be leveraged, basically. Now, let's look at one particular SDG, and actually one area of SDGs, starting with SDG 11 on sustainable cities. All the SDGs, all the targets from SDG 11 can be positively affected by AI. So this is an area where really AI can help us a lot. And I focus on the area of pollution in cities. So it turns out that 800,000 people die every year in Europe only due to exposure to pollution, basically. And this has implications on SDG 13 as well in climate action. So there's technology that we can use to try to, alleviate to some extent the problem of pollution in cities. And this is more of my technical work, so not more focused on my main area of research is actually fluid mechanics. So that's what I'm an expert on, of course, with some implications on sustainability. So we can simulate with quite some accuracy urban environments. These are very, very detailed simulations. And the idea is to use sparse measurements, and you can get more details of the simulations in these references by Lazpita, Martinez Sanchez. So basically, from these sparse measurements, we can use neural networks to reconstruct the 3D flow in the urban environment, the 3D velocities, the 3D fields of temperature, and also the pollution levels. So that's a bit something that we can use to determine what regions of the city are exposed to higher levels of pollution and what type of actions can be taken there. Now, this can be done in different ways. On the right, you can see the level of detail of the simulations that we have. So we can actually change the geometry, change the separation between those buildings. That will change the regime that you can observe in the urban environment and the type of turbulent features that you can find there. And then through different methods, different model decompositions, and reconstruction tools, you can actually obtain, I would say, pretty good reconstructions of the field from the sparse measurements. Right? So that's a little bit the idea of what we can do here. I would like to also argue that AI is helping us in the tools to simulate these flow fields. So this is a review paper in Nature Computational Science that came out a couple of years ago, where we argue that machine learning can help us to accelerate simulations, can help us to perform better models of those simulations, and can help us to develop better reduced order models. And these reduced order models are very simplified simulations that contain the essential physical ingredients and that can be instrumental to be able to understand the characteristics of the flow in these urban environments, but also to try to get good insight into strategies to reduce the pollution levels. So everything that I talked about so far had to do with the big picture, right? Kind of like how AI globally is helping us with sustainability. Now I'm going to get a bit more technical on some tools, on deep learning models. So I don't know if the audience, this is a bit too technical for some of you. I will not go into too many details, but then I will leave enough time for questions if you want me to go deeper in some of them. So when we are looking at predicting the flow in cities, right? That's the technical solution that we're talking about here. One can use fully connected layers, right? Like this multi-layer perceptron that you can see here. But this has the problem that in images, you want to be able to exploit the spatial patterns that you have. And of course, the flow in cities, as we can see here, there is these concentrated regions of flow movement that we want to be able to exploit to make our predictions. So there's a different type of architecture, the so-called convolutional neural network, which is the simplest computer vision tool, which are able to exploit through convolutions the spatial features in the data in such a way that we can effectively make predictions of the flow. And these tools, I mean, you can see here this little window, that's a kernel. So this little window is sweeping through the input, and then by applying the convolution, each value in the output here receives information from 9 inputs, basically. So through this approach, we can actually get quite robust predictions of our data. Now, this is an example of how to use this in a simplified urban environment. So basically, I have sensors at the wall, that's the blue surface there, and I want to use this information to predict the flow above the wall to see what's happening above, no? So at a certain distance from the floor. I can use, this is published in the Journal of Fluid Mechanics, I can use convolutional neural networks to exploit the spatial features on my input data at the wall and effectively predict what is actually happening above the wall. Okay? That's a little bit kind of like the idea of what I'm showing here. And it turns out that a convolutional neural network is very nicely adapted to flow predictions in a city because, and I'm going to explain you a little bit how it goes. Here, what I'm having is a schematic representation of a convolutional neural network where my input fields are on the left. These are two-dimensional fields measured at the wall. My output fields are at the right. Those are 2D fields measured above the wall. And what we have in between is a number of, in particular, we have 6 hidden layers with a number of convolutions. So these convolutional neural networks in the first layers are identifying features, elements in the data that are very simple. And then due to the concatenation of nonlinear operations, as I go deeper into the network, I am hierarchically building more and more complex features. That's a little bit the idea. That's how this works. So we can exploit the possibilities of exploiting, of analyzing features and localized data from convolutional networks to build my flow reconstructions. So that's a little bit what it looks like. I have at the wall 3 measurements, and this is the wall of this simplified geometry. And above the wall, I'm showing you these 3 planes that you can see here. These are velocity fluctuations that we can measure. And of course, these fluctuations of velocity are helping us also, I mean, we can as well predict temperature and pollution levels in this realistic turbulent flow scenarios. We also use another method which basically combines convolutional networks with proper orthogonal decomposition. Basically, CNNs with proper orthogonal decomposition is PCA, or principal component analysis. Turns out that by combining both methods, with the PCA, I can encapsulate the most important information in few modes, few modal representations. And with the CNN, I can exploit the spatial information in my input to predict the temporal coefficients of those modes that are dominant in my physics. And this is done in a way that I can obtain very good predictions even far away from my sensor inputs that I have in my city. So what I'm showing you here is an instantaneous snapshot of the flow. In the first column, I'm showing you the data close to the measurement plane. And in the second column, I'm showing you the data far away from the measurement plane. The third row would be the reference. So this is what I'm targeting. And the first row is a prediction made with a linear method, a so-called extended POD, extended proper orthogonal decomposition. Turns out that, and this is important to keep in mind when I was talking before about the physics of the problem, the flows in series are highly non-linear, very chaotic, very high dimensional. So if you use a linear method to make this prediction, you're going to only be able to reconstruct part of the physics. So the errors are actually reasonably high. When you use neural networks, you're exploiting the nonlinear activation function to reproduce some of those nonlinearities present in the flow, right? Present in the city. And we can see by comparing the last row with the third row that close to the wall, the convolutional neural network works extremely well. And far away from the wall, that would be the second row, what we see is that the combination of convolutional network with PCA works much better. So we are able to encapsulate the relevant information from the flow fluctuations into a few of these modes, and then the convolutional network can predict the temporal coefficients quite efficiently in this manner. One last comment has to do with transfer learning. This is a quite important thing to keep in mind. So if you remember, I was talking about the big electrical consumption of these AI models, and the fact that if we know something about the problem, we should embed it in our model. We can also do transfer learning. And in transfer learning, what we are doing is apply a model that is used for one particular task to another task that is not so different from the first one. In this case, we're using a model trained at a low Reynolds number. Here, I don't want to get too technical on the fluid mechanics, but basically in a not very turbulent condition for a very turbulent condition, a much higher Reynolds number case. What we realize is we first train a network with random initialization for the highly turbulent condition, and that gives pretty good results. Then we took a network trained at the low turbulence condition, and we transfer it to the high turbulence condition and add a bit extra retraining. So that's the transfer learning. We add some training. What we realize is the network transfer from the low Reynolds number required only 1/4 of the data compared with the network where the initialization of the weight was random. And what does that mean? That means that in the low turbulence case, there were some features, there were some elements that were also present in the high Reynolds number case, which means that we can exploit that in such a manner that we can effectively do this transfer learning. Not only that, what is also interesting is the fact that in the high Reynolds number case, to produce data is significantly more expensive than in the low Reynolds number case, in the low turbulence case. We are talking on the order of several hundreds of times more expensive. So the data for the low turbulence case, I can produce it with a laptop. It's actually quite cheap. The data from the high turbulence case, I need a supercomputer with on the order of 2,000, 4,000 processors to produce the data. Now, if I can reduce the amount of very expensive data to 25% of the original, and I can reuse a lot of cheap data to train my models, then I'm certainly doing something good for the sustainability of this model, which I'm in the first place using for sustainability, right? So to keep a good idea of the environmental footprint of these models is essential, which means that we need to keep, on the one hand, the application of what we know about the system and embed it in our model, and second, use transfer learning to effectively exploit what we have already trained, right? We don't need to retrain things that we already know in a new configuration. So transfer learning, I would say, is key to developing sustainable AI systems, basically. I also wanted to talk a little bit about another computer vision architecture, which is the so-called GAN. So far, I've been showing you convolutional neural networks, but GANs, which stand for generative adversarial networks, are actually quite interesting too. GANs are very good at reconstructing data from sparse measurements, so basically increasing the resolution of images. In a GAN, you have two parts, the generator and the discriminator. The generator has the role of producing, in this super resolution task, high resolution images from low resolution data, which basically reproduces the statistical information of the original data. So the generator is able to produce fake data that is realistic. And the discriminator has the task of assessing whether a particular image is real from the original data set or it was fake, it was produced by the generator. And of course, these two networks are having antagonic roles. They're trying together using game theory in such a way that you create a generator that is extremely good at producing realistic images. What we did was, starting from wall information, the sensors that are very sparse, so very, very sparse data, with the GAN, first increase the resolution of the wall, and second, apply the prediction in high resolution. So that's a little bit what we are doing. And what I'm showing you at the bottom are some predictions. Under DNS, you see the real flow, the real field. And in the top row, the top line, I'm reducing the resolution by a factor of 4, 8, and 16 squared, respectively. You can see in the 16 panel that the resolution is so low that I can barely identify any of the features of the original data. And in the reconstruction on the second row, you can see that I can obtain a very realistic, very physically looking flow field. In fact, the structures are where they need to be. They have the right size and the right locations. So GANs is really helping us to make predictions of the flow in a city from very sparse measurements, basically. And nowadays, this was published 3 years ago. Nowadays, we have more modern methods with diffusion models. So we're able to get very, very good results in high dimensional 3D fields, but GANs are a very good place to start in terms of this flow reconstruction. Okay. Let me see. Good. So this is a summary of my talk. I want to leave enough time for questions because I'm sure that there will be different aspects that we can discuss a bit more. In general, AI can help 79% of the targets, but can be an inhibitor of 35% of them. So there is a very much needed global debate. CNNs and GANs are very valuable tools to make predictions in cities, and we are actually able to obtain very good accuracy in terms of this reconstruction. We're using AI for developing policy decisions. So that's actually quite a new thing that we believe is quite relevant. And this is my contact information. So you can always contact me by email, by social media. I have a YouTube channel where I am giving lectures about AI, about dissemination, about some of these aspects, some scientific applications of AI to sustainability. So feel free to check more videos there. And also to reach me out anytime if you want to discuss or share ideas. For now, that's all for today, and I'll be happy to answer your questions.
Well, thank you very much for this very, very nice talk. So now it's time for questions from the audience. So as usual, feel free to write your name in the chat and I'll give you the turn to speak. Are there any questions? No? Well, so I can ask you something, Ricardo. I have a couple of questions for you in any case.
Mm-hmm.
So the first one will be, if you could tell us a bit more about the policy-making impact of your work on the role of AI in achieving the SDGs. I mean, is actually EU using your research to implement laws and regulations related to AI? Can you give us more information about this?
Yeah, so the original work, which is just a list of examples of how AI can impact the different targets, that was discussed in the European Parliament when the AI Act was being developed. So many examples were quoted, many possible negative implications were discussed. So let's say that that work helped to inform some of these decisions. My more current work using NLP and LLMs to analyze the SDGs, that's, I mean, we haven't finished it, but the goal, which is maybe a bit too ambitious, is to shape policy decisions. So if we are able to understand how the SDGs and the targets are interconnected, how can I make policy decisions such that I can leverage all the synergies and I can avoid the negatives? No, that's a little bit the idea. So we're really taking advantage of the power of these very, very large models to read a lot of data and to organize all the data. No? And this is something that we're doing together with Google Research. So we're having the possibility of accessing some of these very large LLMs that they're developing there. Yeah.
Okay, very interesting. Thanks a lot for the answer. So what was the most surprising conclusion for you when you started that research on the role of AI related with SDGs? I mean, you more or less were expecting all the main outcomes of your research, or did you discover something that was really counterintuitive and surprising for you?
Yeah, that's a very good question. So, of course, some of the examples, concrete examples, were a bit surprising, no? and nice to realize that there were some interesting things that were being developed. But the overall conclusion was not very surprising. No, I mean, I guess we could have an idea that there was overall quite some potential, but some danger. No, and quantifying the potential and the danger, that was kind of like the nicer outcome. But I think I was probably a bit surprised by the research gaps in the negative effects of AI on the environment and the society. So in particular, if I go back a bit, because that's, since we have time to discuss a bit, I think that's maybe what surprised me the most. I thought that because it feels that there is quite some awareness, no? That there are some risks that we need to take into account. But when we looked at the studies and classified them into A, B, or C, D, we realized that they were quite speculative, that everybody was saying, yeah, there's a risk on the society and the economy, sure, but it was not such strong evidence. You know, we classified them into these 4 categories, and I'm talking in particular about here in this right panel, the difference between the light color and the dark color in the environment and the society. So I think, I mean, I can quite easily give reasons of why there are negative effects, but they are still a bit speculative, and there's much more research to be needed to really quantify and assess those risks and establish them in a way that we can do something about it, basically.
Okay. Thanks a lot again. So we have one question from the audience. Nasser says, well, thank you for this interesting talk. I'm just wondering, what key areas, domains, do you think current AI ML community is overlooking that could be crucial for sustainable development in the short term? Let's say the next 3-5 years, and why is that?
Yeah,
thanks again for this great talk.
That's an excellent question, Nasser. I mean, I believe there is a lot of potential from AI for sustainability in general. And I think this policy development that I'm talking about is a very big key. If the biggest thing that is being overlooked is the environmental cost of these AI models. No, so transformers, which are the self-attention mechanism in transformers, which is the underlying technology of large language models like ChatGPT, deep down, and we have spent some time looking at these attention mechanisms and developing new attention mechanisms. This is work by a PhD student of mine, Marcial Sanchez, who is looking at improving the attention mechanism of transformers. It's a bit of a dumb model. I mean, it's quite simple. It's at the end an SVD with a nonlinearity. That's it. So they work because they are very large and there's a lot of data, right? And they put them in thousands of GPUs and that's it. I think we are overlooking the power of simpler, smarter models that can have a lower environmental impact, that can have maybe better accuracy, and that we can improve our performance not by throwing more data into the models, but by thinking a little bit more what these models should be doing in reality. So that's a bit what we are trying to understand here. Yeah.
Okay. Thanks a lot. So any other question from the audience? Because otherwise I have the very last question. I don't know if anyone else has any other question. Apparently not. So Ricardo, my question is related with the last part of your talk, related with flow or turbulence prediction. I mean, I've never tried on that particular problem, but I would like to ask you if have you tried some sort of recurrent neural networks? Will that make sense to work with recurrent neural networks? I'm asking this because I will think that there's some temporal dependency or, I don't know, feedback between different time steps in a sequence. I don't know.
Yeah, that's a good question.
Would that make sense? Yeah.
That's something that we did quite some time ago. In 2019, we started to look at turbulence and try to make temporal predictions. And we compare MLPs, a very dumb MLP, with GRUs, gated recurrent units, and LSTMs. So the LSTM works well. If you optimize the parameters and so on, it works well. However, it has one problem in the context of turbulence, and that's why transformers, for example, are working better. If in a recurrent network, of course, what happens is that all the steps are connected, right? So one step is connected with the next one, and the next one, and the next one, and that helps you to learn the temporal dependencies. But in turbulence, you have a quite pronounced multi-scale character. So you have things that are very large and very slow, and things that are very small and very fast. So the small and fast things can be predicted quite well by the LSTM, but sometimes you have a very large feature that has an impact many time steps into the future, right? And that's going to be lost by the gating mechanism of the LSTM because, it's being recurrent and the importance of the samples is going down with time, you really lose the effect of these very large things. Attention mechanisms of the transformers, and again, it's not a very smart system and we're trying to develop it, but these attention mechanisms are able to find correlations of the data wherever they are more or less in the input sequence. So if there is a very slow thing way in the past that is affecting the present, and there is quite a strong correlation there, the attention mechanism will see it. So for temporal predictions of turbulence, right now, transformers are the network or the architecture that is working the best.
Okay, thank you very much. Your last chance. Any question? No? Okay, so I think we can end here this DaSCI seminar. I want to thank you, Ricardo, again for accepting our invitation and for giving this extremely interesting talk.
Thank you very much for the invitation. It was a real pleasure.
Thank you. And of course, also thanks to all attendees for the questions, comments, and attending this talk.
Take care. Have a good day. Bye-bye.
Bye-bye.